The heat of the air, the heat of the ice, the temperature of the brine, the electrical used. It's also tracking the time of day, or the ambient conditions, and it's logging so we can log on here. We can look at it and instantaneous at any moment what's it at in this arena, as well as the trend data, what's it been doing. And that trend data is very important to have. Well, what was the day like? Because it makes a big difference on, well, today we had twice the heating demands we had the same time last week. Well, why is that? Well, because last week it was 10 degrees and today's minus 25. So that's why it's important to get that kind of trend data. And this is something that we've got as an obligation to SaskPower to collect this data for their program.
Do they supply the tools to
yes.
get measured as well?
Well, they assisted us with hiring the consultants and hiring the contractors. Okay, the next step, kind of building on that, is a pilot project, again with SaskPower, that we're doing at the Cosmos City Center and the Credit Union Center. And it's called IceMax. IceMax is a bacteria called Pseudomonas syringae. And what it is when this bacteria this bacteria forms with a special protein molecule on the outside shell. So by putting this dead bacteria within water, because of the shape of the molecule, it actually promotes water crystallization. Water's got a very unique molecular structure. It's one of the few things that you think, when they cool down and solidify, they shrink, the water actually expands. That's because of the unique crystalline shape. So by affecting the actual physical properties of the crystals that form, you actually can change the temperature it freezes at, or how rapidly it will freeze. So the question, does water freeze at 0 degrees Celsius? Well, first of all, the answer would be pure water does, but when you add impurities to it, you actually start lowering the freezing point. The more minerals you have in it, if you think the ocean doesn't freeze at 0. Why? Because it has a lot of salt in it. There's other things, even after the water comes through our water treatment plant, there's still minerals, there's still chemicals in it that all help lower that temperature. So it actually, because of that, water will freeze someplace between -3 and -8 degrees Celsius, depending on where you are, what your water quality is. Now the idea is, the higher you get that freezing point, the less energy it takes to get a good ice surface, and therefore the less electricity demand, the less greenhouse gas emission. So this is like a pilot that was done down in Vail, Colorado. This yellow line is the curve that the temperature they require to get the good ice formation under normal circumstances were. And you can see, like, the ice actually only starts really forming at like -23 degrees Fahrenheit. You didn't get a really complete freeze in a significant amount of time until that's about -14 degrees, which is, 14 degrees, which is about -10 degrees Celsius. So that was what they had to set their set point in their ice sheet to make sure it got good freezing. When they introduced this bacteria, right away at 27 degrees, they had almost complete freezing. It's like kind of the magic number, and that's at about -3 degrees Celsius. So they got an improvement of 7 degrees Celsius just by introducing this bacteria. So what's the results, or what are the results we're expecting? Well, we're going to be conservative. We're going to estimate or hope that we can get between a 1 and 3 degrees Celsius rise in the freeze point. This will reduce our energy load for refrigeration. Another thing that this bacteria does is, because of how it promotes the freezing, you can use cold water or cool water when you're cleaning the ice surface with a Zamboni. Normally you need a warmer water because it has to like melt the cracks in the ice and help it flow together. With this, the cold water can seep into the cracks, lay a surface, all freeze at a uniform time, and make a good skating surface again. So you don't need to heat the water. So by not putting hot water on the ice sheet, you reduce the cooling load again of the equipment, and you don't have to heat the water. So it's kind of a double savings. As well, this extends the longevity of your chillers and your pump. So the less you need to use the equipment, the less hours a day that you need to use it, the longer its lifespan will be. Because if, let's say, a piece of equipment has a lifespan of 10,000 hours, well, cutting your use per day from 10 hours to 8, you've just increased the lifespan of the equipment by 20%. This IceMax is completely safe for people in the environment, so there's no concern with, like, when the ice melts, you put it into the sanitary sewer, that's perfectly fine. Same thing when you clean the ice and you leave the piles of snow outside the arena, you don't have to worry about that melting, getting into the groundwater or into the water table of the river. It's perfectly safe. All the bacteria is dead already. As well, this is a process that's introduced into the water and the Zamboni itself when it spreads it around. So you have it in your initial flooding, and then the Zamboni, you just add it as an additive to the Zamboni water to maintain your sheet.
What's, Chris, what sort of concentration of the bacteria?
I don't know that. I don't know how. I know it comes in, it's like a white powder, small packet. A small packet you dump into the large tank of water. Now what the actual percentage is, I couldn't tell you, but it doesn't seem very significant.
What's the cost like on it?
I don't know that number either. But we've been told by the consultant, by the people that are selling the product, that we should be able to do at least a 20% reduction in our costs, and that should pay for itself, and it should pay for itself in 5 years of the general process. But let's see. Next is a project that we've got. This is with the facilities group. This is actually the facilities department within the city's main project at the Saskatoon Fieldhouse. At the Fieldhouse, they've got very old boilers. They're 30 years old. The older a boiler gets, it starts running a little bit more inefficiently, so there's the extra energy loss. There's an extra demand on maintenance, ongoing maintenance costs, as well as the reliability drops. So it becomes a liability for maintaining temperature that you're providing to the users of the facility. So, end of their service life, it was time to replace them. We came on board as kind of an advisor, helping them negotiate, design the system, as well as when they put in the system, we helped get some monetary grants through green energy loans for them to put this in. After all, it's $22,500 savings per year on energy costs, and we got them $57,000 in grants to help them put in the system. And the new system's a hybrid system. There are two types of boilers, two main types. There's condensing boilers, having a maximum efficiency of about 95%. There's non-condensing boilers, which are 80%. And this is what the older technology, so most facilities are designed with non-condensing boilers in mind, and that's what we had at the Fieldhouse. So what we've put in is a hybrid system, a non-condensing and a condensing type boiler. Now the question I always well, if condensing boilers are 95% efficient, why don't we just go with a condensing boiler system? Well, if you look at a facility, so you've got a boiler that's trying to heat an airspace in a building. The boiler heats up water to a certain temperature. That water goes through some sort of heat exchanger to heat the airspace. When it does that, it gives off a certain amount of energy, and the colder water gets returned. General philosophy. And that colder return water is the inlet temperature now back to the boiler that it has to heat up again. For a condensing boiler that has a very high efficiency, to achieve that efficiency, you need a very cold inlet temperature. So as long as your water's coming in nice and cold, it heats it up, all that energy gets pulled out of the water, it comes back cold, and that's where your high efficiency comes from. Now, the issue is, you need that water to be coming in cold. To do that, you need a very large heat transfer service. So for a facility to be designed for condensing boilers, you need something like in-slab heating, something where you've got a very large surface area that you've got the waters running through, you have lots of time to give off its energy and come back. Now the Fieldhouse and many other facilities are designed with forced air heaters. You've got coils going through an air fan, so you're blowing this air across. You've got a very small heat transfer area. Smaller heat transfer area means you need a much higher temperature difference between the fluid that's doing the heating and the air itself. So even with the Fieldhouse, we're finding if we're not needing too much of a heating demand, as in the day temperature is relatively warm, or even say 0 degrees Celsius, the water's coming back cool enough that a condensing boiler is still the efficient way to go. However, when it gets really cold outside, say -20, that's where, to get the heat to do the airspace, we're getting water coming back at 70 or 80 degrees Celsius. And for that, a condensing boiler becomes very inefficient. So that's why we've got the hybrid system. The non-condensing boiler picks up the load at that point. The non-condensing boiler works very well with high inlet temperature, or well, better comparatively. So by doing the two in conjunction, we get the best savings for overall. The ideal thing is when you build your facility, design it for that large heat transfer space. But if you have to retrofit, a hybrid system works the best. The next project is Saskatoon Light and Power's project, solar hot water heating for their domestic hot water system. Now again, this is a Saskatoon Lake Power project.